All right, I think we're going again. Okay, so here I've drawn up a circuit. We have a voltage source that has 66 volts. R1 is 2.2 kiloohms, R2 1.5 kiloohms, and R3 is 2.7 kiloohms. Now, one of the things that we're going to do is I want to find what is my R total, what is my current total, what's the power total, the voltage drops across all of these guys, the power across each one of the individual components, and then we'll talk about this next set. These are specific dual subscript notations. Okay, basically what they're telling us is these are what I want to measure. So for VR1, this is saying I want to measure the voltage across R1, voltage across R2. This case, I want to measure the voltage from point A to point C. So that means you're going to put your positive on point A, your negative on point C. And let's add one more. We'll flip this one around as well. So basically when we're looking at this, when it gives us the letters and we have test points, you put your black or your red probe on the first one, your black probe on the second one. If it doesn't give you one, you go to the ground. So if it just says from point C, or the voltage of C, you put the positive on C, your negative on ground, the black probe. If this is not given to you, assume the negative of your power supply. If there's multiple power supplies, there usually will be a ground, because that does then matter where you put it. And we can go through and then we'll even shift these guys around a little bit and show the difference that it creates. Okay. So as we go through and we're going to solve for this, I have a little cheat sheet on the board behind me that we're going to write down our answers, just so we can keep them off to the side, because we're going to be scrolling through this pretty far and I don't want to be going up and down and up and down. But this is where we'll go. In the quiz, it's going to give you answers like this to fill out. It gives you the unit that they should be in. I say the majority of the time there is no issues. Once in a while, one of them sneaks through that didn't match up, that didn't convert over correctly when I imported these quizzes. If that does happen, let me know. But I would usually side on the option that these are correct more so than that they're not. I'm not saying that there isn't any issues, but use those as this is my answer. If you get something in a different unit, you might be wrong. Most of the time, that's going to be the case. Okay, so the first thing I want to do is I want to find my R total. In a series circuit, how do I find my resistance total? Add up all the resistors. Okay, what about my current? What's the current? How do we find the current, or what's the current in this circuit? Voltage total divided by resistance total. And it's going to be the same everywhere. Power total. What do you guys think? We didn't really talk about that, but what do you guys think? Voltage total and current total. Then the individual voltages. So we know that the individual voltages are going to add up to be this total voltage. What about powers? What do you guys think about that? Current squared times resistance. Also, these powers are going to add up to equal our power total as well. So powers add, resistances add, voltages add, current stays the same in a series circuit. Okay, so our R total, we solve by adding up all the resistor values. So it's going to be 6.4 kiloohms. And we get that by adding R1 plus R2 plus R3. So 2.2K plus 1.5K plus 2.7K. Yes. Okay, so there's our R total. So let's record this down. And we matched the unit that we're supposed to have. Does everybody agree with the 6.4? Okay. We have our 6.4. Now we need to go for our current total. Morgan, what's our current formula? Yes. Okay, which gives us So I do apologize when I'm writing these numbers up there. If my decimals look a lot like commas, that's just because the board doesn't like just little dots. I have to exaggerate them. I try not to write values out where I'll be using a comma and a decimal, just so you know. So if there's a question, please feel free and ask, but yes, this is supposed to be a decimal, not a comma. Okay? Do we agree with that value? Okay, 3 and 3. That is our current total. Find that on our board. And again, our units match with the answer that it wants. Okay? Now we need to find the voltage drop across R1. Again, we can do this one of two ways. Current divider, voltage divider, or we can use the current. So Carson, where are we at? Okay. That was you, right? Was that your Carson, right? Okay. I wanted to make sure I got the name right. That's why I was kind of hoping if they responded when I throw the name out. How do we want to solve for voltage? Yeah, voltage of resistor 1. So I1 times R1. So we get the 10.313 milliamps multiplied by 2.2 kiloohms. And Carson, what do we get? Do we agree or disagree with that value?
So I tried it with the voltage divider, and
okay.
I got the right number, just way too late, so I got 22,666.
Okay, so let's look at that. So that's how we solve it using the current. Using voltage divider, we take the 66 volts, write out the formulas. Voltage total divided by R1 over R total. So the 66 volts multiplied by the 2.2K over 6.4. My guess is you didn't have one of those K's in there.
Yeah.
But here's the good thing though. When we're looking at this value, what can we do with this number? Can we reduce it at all just by looking at it? How? If we have a 10 to the third on top divided by a 10 to the third, what does that become? 10 to the 0. So we can throw the K's right out. So if we have both kiloohms on the top and the bottom, we now can reduce this when we're plugging this into our calculator as just 2.2 divided by 6.4. So we can save ourselves a couple of steps that way. Okay? So then that should end up back down to your 22.688. Yes? You can convert it. So for right here. So this one, remember, we have 10 to the negative third times 10 to the third. When we multiply powers of 10, we get 10 to the 0. Okay, so we got VR1 Zach, what's my VR2? 649? That's why I asked. Okay, and how did you get that answer?
I didn't use the.
You just use voltage times current? Okay, our current was 10.313 milliamps multiplied by the 1.5 kilo ohms. So you said you got something different?
Voltage for resistor 2. They have 2.4.
Oh, yes, Mr.
Okay. Is that closer to what most people got? Okay. We're still within the ballpark. It can be how you rounded off your values, that kind of stuff. Okay. It's the value I got when I typed it into my computer too, or calculator. So now, yes. Quiz has tolerance taken into account. So there is the correct answer, and then you can be within 5% of that answer and still get it correct. But just know there are times where you're going to use that number and it's going to, go through another set of calculations. So by the end of it, if you're too far off at the beginning, you could drift out of tolerance by the end of the quiz. So there is times that can happen. Okay. Oh, geez. Really? Now we need to find VR3. Max, what do you got?
I got 27.844.
844? And how did you get that?
So I took 66 volts times 2.78 ohms divided by 6.4 ohms. And 2.7 divided by 6.4 is 0.421875. And when you multiply that by 66, you get 27.8435.
Okay. Agree, disagree with that value? Okay. The other way you could have solved for that value as well, we know the voltage drops have to be equal to the voltage source. So we could take the 66 and subtract our drop here and our drop here would give us the same answer within a few decimal places, depending on how we round it off. Any questions about the voltages? Okay, now let's solve for our powers. Now, we want to solve for the power total. So what's our formula, Kaylee, for power?
For power, isn't power the same thing as, isn't it the same thing as energy?
Yeah. So power. So on that chart, V and E are going to be equal.
Okay, so then it's,
What times what gives us power?
I times 8.
Hmm?
I times 8.
Yep. So power is current total times voltage total. Because in this instance, we're dealing with the total. Okay? So we have 10.313 milliamps multiplied by 66 volts. And what does that answer, Kaylee?
68.06.
Okay. Make sure you're putting in the right value. 10 when you're entering it into your calculator is that. Yep, or 6.6. We good there? Okay. So we end up with 680 milliwatts. Not a lot of power. You know, good size amount. Your resistors are going to start feeling a little warm. You know, you can kind of see it, you know, feel it a little bit. Definitely nothing that you're going to see smoke coming off of them or burning the dust off of them, that kind of stuff. When you get into the 3-4 watt range, then you'll start smelling dust burning if the resistor is hot enough to handle it. Especially when we start doing power supplies. Some of the power resistors have quite a lot of dust on them. They just don't get used a whole lot, and when they get hot, it starts burning off the dust. And you think you're losing your circuit, but all you're doing is just burning the dust off of them. It can get fun. So this is crank up the heat. Unfortunately, I think you'd have other problems if your house was getting that hot to burn dust. Okay, so power across R1. Let's go with Spencer. Let's go ahead and solve for this. Resistor 1. So that's the other reason too, is so if you can't find it in your notes, we have our cheat sheet up on the board as well. What's our formula for power? Voltage, okay? So the current through these guys are going to be the same here. So we're going to have the 10.313 milli. And that's going to be multiplied by the 22.688. And what value does that give us, Spencer? Okay, so 0.233 or 233 milliwatts. Which then, let's check, the power across R1 is in milliwatts, and we're still good. The other thing to check is we should kind of see a similar ratio and a breakup between the power and the voltages. So where this guy is the 2.2K, we got this much. When we do our 2.7K, we should see slightly more power. When we get to the 1.5, we should see a lot less, just because of the ratios of these guys. Okay? Power of R2, Seth. which is just what we would expect. R2 is the smallest resistor. It's got the smallest power. Let's see, who haven't I picked on yet? Jessica. Solve power for R3. Like I said, we should expect to see a higher power than that guy. Milliwatts. Yep. So then as a quick double check, let's just add these guys together. So we have 233 milliwatts, we have 159 milliwatts, and we have 287 milliwatts. Gives us 690 or 679, and we're 680. So we're within a milliwatt of power. And that's just by rounding off a lot of the numbers too. Okay? So we end up with those totals. Now let's come back up to here. I'm going to throw our voltages onto these guys. So now after we've designed our system, we've got our powers, we made sure everything's going to work fine, we're not going to burn anything up. The biggest thing that we need to worry about is, like I said, with the powers. So when we come down here and look, we've got 233 milliwatts. That's approaching a quarter watt. If we get very big fluctuations in our current, this is going to go over 250. So we should probably make sure that this guy is at least a half a watt resistor. So a bigger size. And I'll show you those in lab when we get into there on the different sizes that we have.
And those are still, like, you can still get any ohms.
Yep, all it is just the physical size. How much heat can it handle before it gets destroyed? This guy, we can get away with using a quarter watt resistor, 250 milliamp or milliwatts. This guy, we have to use a half watt resistor. There's no choice. It's going to be over that threshold. So that's why we have you do power, is so you can understand, are things going to burn up? Can I get away with the cheap, smaller one? Is if this is all I have, will it work, or am I going to potentially lose it? And I'm not going to say just because you go over 250 milliwatts, it's going to immediately burn up. But I'm not going to say that just because you don't actually get there, it's not going to burn up. So remember, there's a little bit of tolerance either way. When you start approaching one of those boundaries, it's easier to err on the side of caution and go up a size as far as wattage. It's not going to change any of your values. So let's say we have the circuit built. This is part of our test board. So we have this chip that comes in, or this board that we plug in, and it gives us these voltages for whatever we may need them for. Whatever our customer designed this thing for. Well, when we build this, a lot of times what we're going to do is external to the tool, we're going to have test points that we can measure. We can stick our meter in and we can measure them, and they're going to give us values, a whole big long schematic, and they'll say at test point A, you should have 15 volts. At test point B, you should have 12 volts. At this test point, you should see a clock pulse type of a thing. So it makes it so you don't have to get into the circuit board, because a lot of times they put the circuit boards in and they're stacked like this. So you can't get into the one in the middle with probes or even barely look down the slots. This gives you test points to find out, is this thing working like it's supposed to? Or a lot of times you'll calibrate stuff so whatever test point is a specific value. So that's where these come into play. These are test point measurements. So on this, if I was going to measure these points, first thing I'm going to do is put my probe, red probe there, black probe there on my voltmeter. And then we're going to compare it to the voltage of these guys. So when we have these, what is the polarity of R1? What comes first, positive or negative? Positive. Why? Because it's closest to the positive terminal. Okay, we're going to have a higher potential energy on this side than we do on this side. So the polarity of this resistor becomes that because of the voltage. Inherently, it doesn't have a polarity, but because of the voltage, it gains a polarity. What about R2? Positive then negative. because it's still based on this guy. R3, negative, positive if you're looking at it from left to right. Okay? So now basically what we're going to do is the other thing we want to check is we want to check our Kirchhoff voltage loop. Make sure everything comes out to be equal. So what we're saying is we're going to start here. We're going to go around. So our KVL, this is kind of our double check to make sure that everything balances out. So what we should get is at the end of this equation, it should equal 0. Okay? Whatever is in is what's being used. So we start here and we're going to go around the circuit getting the voltages. So the first thing we run into is a negative 66 volts. Okay? Then we come around the corner and we run into a positive 22.68. Then we run into positive 15 volts. Then when we keep going around this corner, we run into and then we're back to where we started. This is just a double check to make sure the math and everything that we did is correct. So if we plunge that all into a calculator, what do we get? Should be close to 0. My guess is it's probably going to be plus or minus 5 millivolts. Exactly 0? Okay. With our KVL with that, we know we did this correct. Okay? A lot of times we'll come back to this, be giving a couple of voltages, we know our source voltage, and that's how we'll go back through and design the circuit, is by using our Kirchhoff voltage loop. We can find out what these voltages need to be. Okay, so now coming back, same principle with these guys. So we're going to measure from point A with the positive to point C with our negative, and we're going to find the voltage. It quite literally is, you start from here and move and add and subtract your voltages as needed till you get to C. And it doesn't matter which direction you go. That's the cool thing. So if we start here, we're going to go to C. The first thing we run into is a plus 22.688 and a plus 15.468. So what voltage are we going to get when we measure from there to there? Nope, because we're just going this direction. We're just going in a straight line from here to there. Zach? 158? 38.158? Is everybody else getting the same value? Okay, let's go the other direction. So we come from here, and we're going to go down this way and across. So we run into is a positive 66. Then we run into a negative 27.844. Wham bam, there we go. Okay? So now that could be one of our test points in our schematic diagram or of our circuit when we're trying to calibrate this thing. We could have a potentiometer somewhere in one of these resistors that we calibrate it until we get this voltage. Okay? So let's go from B to D. So again, positive probe is going to go on B. Negative probe or your black lead is going to go on D. So you run through a positive 15.468 volts and then a positive 27.844 volts. So what do we get when we go from those two test points? $392? $312. Do we match? Okay. Now, the next one says VC. So this is only giving us 1 point to start from. So we know that our positive probe is going to go here on C. The black one, where's it going to go? On ground, because it's not given to us. So in this case, we go from positive to negative, and we run into 27.844. And that's it. That is the test point voltage for that. Because that's all we have. We could also go the other direction. If we went from C to ground, we could go up. We have a negative 15.4, a negative 22.6, and a positive 66, which is then going to give us a net of positive 27 volts. Okay, this last one, VDB. So in this case, we're putting our positive on D and the negative on B. So what are we going to run into first? Negative 66 plus 22. So that ends up being just rounding it off because I ran out of space. Okay, that's how we can get negative voltages out of the same circuit. Now there's sometimes that the reason we would want that is we hook this up one direction with a positive voltage. That's going to have our motor spin clockwise. Maybe we don't want to build another circuit to run something going the other direction. Maybe we have a pump, maybe we have a blower. So we have one that's sucking in, one that's blowing out off the same circuit. This negative voltage is going to make the motor spin the other way. And we can do that with one circuit that we've built. So now, and the reason that we would do that is it saves us having to redesign something entirely different. Instead of having two circuits, we have one. And that's kind of the idea, is what can we do to simplify things to make it so we don't have to build so much crap? Because designing takes time. Time is money. Okay, components. Not as much as the time aspect as far as cost, but if you can get two uses out of one device, this is going to get chosen every single time over two separate devices. And a lot of times there's going to be multi-use, multi-function boards within a single component or single system. That's why, like if you buy computers and TVs and monitors and stuff like that, if you buy a computer off the shelf, a lot of the times it's going to have an integrated graphics card, which means that the graphics card is built in to the processor, to your motherboard. So when that happens, you're going to be sharing functionality between the two of them. There's going to be time that your processor is going to be wanting to use memory or stuff that's allocated to the video card, and the video card is going to be wanting to use it at the same time. Well, they have to establish a priority, and a lot of times the processor is going to win out. Your graphics are going to cut out because your processor is using the stuff. Isn't that what? Yep, because you have integrated graphics. And I'm not saying that it's a bad thing. Sometimes if that's what you need it for, that's perfect. But there is definitely benefits of having individual components instead of sharing things. If you don't care, then you can use the one circuit. Any questions about that? Yes. Oh, yeah. So the voltage on D, that's the one thing I didn't really cover. So we're going to go take a look at our picture. We're going to take our positive probe, stick it on D. We're going to take our negative probe and put it on ground. What's the voltage that we're going to read at that spot? 0. If you're ever measuring the exact same point or the exact same wire, they're going to have the same potential. 0 voltage. And even, you could go all the way around if you wanted. Let's just say you just set just offside of D, just offside of here. If you go around, well, you don't run into anything, so you got a 0 there. But then just like with our Kirchhoff's loop, you got a negative 66, plus 22, plus 15, plus 27, you're back down to 0. Pretty slick, huh? Okay. If it's given, it matters. If not, it's assumed to be off the negative of your power supply. A lot of times, so the ground really is, it's just giving you a common point. So once we get into AC, that's going to become a lot more important, because your oscilloscope measures things a little bit differently than your DMM does. You can't just put it straight across a component. It has to be, the grounds have to be in the same place. So then it takes a little bit more effort to understand and determine what your voltages are. But you still are going to measure them in the same style. So the difference being ACs or DC, you can measure directly. AC gets into these test points type measurements. One of the things you could do is, if all you had were these test point measurements, so A, B, C, and D, you could find out what the individual voltages are. So test point B, we have this voltage from here to here. So the 15 and the 27. We know we have 66, so if we know the voltage from here to here, we have 66, we can find the voltage difference between those 2 points. Then that resistor drops that amount. That's how scopes and measuring AC work, is you measure them based on test points versus then actually measuring the components. Make sense? Okay. We're just about out of time, so I'm not gonna lecture anymore, but I'm gonna give you guys something to look at. If you can figure this out, great. We have, or at least tell me give me an idea how this could work, is we want to build a voltmeter. So the schematic for a voltmeter looks like this. But trust me, I know. I saw the scores. There was a lot of people that opened it up and instantly just like finished the attempt. So I know full well. But kind of think about this. Think about how series circuits work, because that's all a voltmeter is. It's just a simple series circuit. I appreciate the honesty. I really do. I really do. So just kind of think about this. You don't necessarily have to go through and figure out exactly how it works, but think about it. Think about how this works. Come with some ideas of what you think, and we'll kind of talk about it and go from there. Because a lot of being in electronics is kind of looking at a circuit and being able to understand, okay, this is going to do something. And so I'm telling you now, this is going to be a voltmeter with variable ranges. Okay, so keep that in mind. Yes.
There's not a power supply because we're hooking it up to a
Yes.
electric circuit that has a power supply. Okay,
That's your red and black probe.
gotcha.
This is your knob on your DMM. These are your ranges. So think about it. Okay, like I said, I don't expect you to come back and be able to explain exactly how it works. But think about this and be prepared to kind of offer an explanation.
Just jump past different resistors, so you're not using this creating a short, not sort of on a.
Keep those thoughts. This is what we'll talk about tomorrow. Okay, any questions about the series circuits from today? Okay, you guys are excused. Have a good weekend. Please work on your quizzes. Get them done ASAP. I mean, not a good weekend, a good day. Yeah. Make sure, like I said, make sure you get your quizzes and stuff done. If you need help, please contact me. Like I said, I'm willing to help you guys with whatever I need to. Make sure if you have outstanding assignments done, get those done as soon as you can. It's better to be either caught up or ahead, because once you start getting behind, you're going to start falling behind fast. Okay. Have a good night, guys. I wish it was the weekend.